Hey everybody, welcome back to another Robinson rant. Yeah, let's get going. Last time we discussed Fourier's theorem, and coupled with that, Fourier's trick. Now, just to give you a reminder, Fourier's theorem states that if we have a periodic function, which I will just call f of t, that periodic function can be represented by the linear combination of cosines and sines, and where m and n are represented by integers. Now, Fourier's trick, is actually determining what the values of an and bm are, such that you obtain the function that you're interested in. And so we apply Fourier's trick to get those values. Now I'll just write it for 1, but the same idea applies for bm, excuse me. So you can say that the coefficient a can be obtained by integrating your function over the period times cosine of a particular frequency. So I'll just label that as p over t dt. And that will give you the pth, if you will, pth component or coefficient. And again, we're going to say that p is contained in the positive whole numbers. And so that's basically the whole thing in a nutshell. So I thought today what we'll do is figure out how to apply this to obtain some sort of more complicated function. Now the cool thing is that the function doesn't even have to be smooth. And so let's go at it. So the function I'm thinking of, the first one I'm thinking of, is what's called the square wave function. So I will define the square wave, this function I'm interested in, as a piecewise function. Namely, it's going to be equal 0 from t is greater than 0, t is greater than 0 to big T divided by 2. So half the time it's just 0, and then the rest of the time, for simplicity, I'll just say 1. Okay? From t over 2 to t. I guess I need to have some sort of greater than or equal to symbol in here somewhere. Okay. So this is the function I'm going to consider. And again, as I said before, if you plot this as a function of time, you will get that it is 0 for t over 2, and then it'll jump to a value of 1 for a period, for a time. And then, of course, after that, one of the things that Fourier's theorem notes is that this is for a periodic function. So although I do not define it for any value of time greater than big T, because this needs to be a periodic function, you could think that at time equals t, it's going to drop back down to 0 for a little while longer, 3t over 2. Then it'll jump back up to 1. Then it'll keep going. So we're just going to treat it on that small range, but we'll see that when we're done, it could repeat indefinitely. Ready for it? Okay, let's get at it. So as I've already hinted at, the big issue here is finding those coefficients a and b. So let's go ahead and see what we get for the a coefficients. Now remember, we've defined this as being the integral from 0 to t of our function multiplied by 2 pi, I'll put pt over t. dt. Now, because we have a piecewise function, I'm going to have to break this up into two pieces. Right? We have defined f of t from 0 to t over 2 as being a value of 0. I'll put cosine of, so I'm going to write this whole rigmarole out for completeness, dt. And then added to that, we'll have from t over 2 to t of 1 cosine of 2 pi pt divided by t dt. And you say, oh, that's simple enough. This first term is 0 because the function is 0. And so I am left with integrating this second function. And so I get t divided by 2 pi p. And the integral of cosine is sine of 2 pi pt over t. And I will have to evaluate this at the limits, t over 2 and t. Of course, now you probably see, right? Okay, we have t over 2 pi p sine of 2 pi p minus sine of pi p. And sine, keeping in mind that p is a whole number, a positive whole number, sine of 2 pi p is equal to 0. Okay? So this is equal to 0. How about sine of pi times p? Yeah, also 0. And so at the end of the day, we get that the coefficient for the cosine term is 0. Okay? And note that this is for all possible values of p. Right? We didn't specify a single value. We did it generically for any p. We could plug in 1, 2, 3, etc., etc. Right? Okay, well, so that's halfway done. We have now figured out that there are no cosine terms included in this expression. Well, now we've better do the sine coefficients. So I'll put BP is equal to 0 to t, f of t. Now, of course, now instead of using a cosine, we need to use a sine. Take a minute. Hack through it. You got it? Good, good, good. Well, let's go at it. So again, from 0 to t over 2, my function f of t is 0, and so I don't need to do anything else there. But the second piece I get from t over 2 to t. And again, we have our sine of 2 pi pt over t dt. Well, let's go at it. We get a t over 2 pi p. And here, we got to think about that for a second. We get a negative cosine of 2 pi pt over t, evaluated at t over 2 to t. Okay. Well, plugging in, we get t over 2 pi p, and we get an expression of negative cosine of 2 pi p plus cosine of pi p. Now, cosine of 2 pi p for any value of p is going to be, 1. Good, good. So we see that t over 2 pi p, this will give me a negative 1 for the first term. How about pi p? Yeah, hopefully you see the second term, cosine of pi p. It has two possibilities. Okay? If p is even, then cosine of pi times p is equal to 1. If p is odd, then we get negative 1. Good. And so we see here, if p is even, we'll get negative 1 plus 1, which is equal to 0. And if p is odd, we'll get negative 1 minus 1, which gives us a non-zero value. So right here, we're going to add in a stipulation. We're going to say p is odd. Okay. We can see that if p is even, those terms disappear. You get negative 1 plus 1. Okay. So if we do p is odd, we get negative 1 minus 1, and we can keep going. So let's keep going. We'll say t over pi times p when p is odd. Okay, now truth be told, okay, now you didn't have to, if you got that far, that's perfect. Okay. Truth be told, I'm going to do a slight modification here. Okay. Rather than having to say p is odd, okay, I would like to come up with an expression that always returns an odd number. And you've probably seen this before. If I give you a value of p, regardless, an integer, how can you use p to always get an even number? Yeah, you probably already know. 2p, right? If I give you, regardless of the integer that I give you an integer p, you can always ensure of getting an even number if you just double it. So that's if I want an even number. How about if I always want an odd number? Yeah, you got it. You take p, you double it, and you subtract 1. That will always give you an odd number. And check it, right? If I give you 1, right? Give you 2, give you 3, etc., etc. Okay. So now let's see here. Do I include 0? I include 0. So instead of doing minus 1, I'll do plus 1. Because p could technically be 0, and then that will give me 1. P is 2, and etc. Just be aware that I am going to do this substitution, and I'm going to do it right there. So rather than writing p, I'm going to write it as 2p plus 1. So at the end of the day, we get that, we'll call it 2p plus 1 coefficient is equal to t divided by pi times the quantity 2p plus 1. So a negative, that bugged me for a second. So what does this mean? At the end of the day, we can now return to Fourier's theorem. F of t equals, we had the summation of an cosine of 2 pi nt over t, but we determined that an is 0 for any value of n. So I don't have to worry about that piece at all. I can get rid of it. That's gone. And for the sine components, right, we wrote, hey, the sum from m equals, I'll put in 0 to infinity, of bm sine of 2 pi mt over t. Okay. Well, now we've got an expression for the coefficients. So now I'll change my index, my summation index, to p. But we can write this as p equals 0 to infinity of b 2p plus 1. So you notice if I plug in p equals 0, I get b1. P equals 1, I get b3, et cetera, et cetera. Okay. So I could put sine of 2 pi 2p plus 1 t over big T. And what do we have here? Of course, I've got an expression for this guy now. So I can write negative t divided by pi summation p equals 0 to infinity of sine of 2 pi times 2p plus 1 t over t times 1 over 2p plus 1. And there you go. We now have an expression which gives us the square wave in terms of a linear combination of sines. And notice a couple of things. We only use the odd frequencies, 1, 3, 5, 7. Okay. The second thing is notice the weighting. Okay. The one that contributes the most is sine. Second most, sine of 3 omega, if you will. Third most, sine of 5 omega, et cetera, et cetera. It's cool, right? Now, don't take my word for it. No. You shouldn't take my word for it. That would be bad. Let's go ahead and pull up Desmos and see if we can actually plot this sucker and show it. Okay? So what do we have? Okay, we have Desmos. So I'll first start off. Let's see here. We have a negative t over pi. Okay, that's, I mean, I guess I could have left that inside the summation if I wanted to. It's perfectly valid. Then we're going to do the sum. And now Desmos requires, I can't choose p. I'll just use n. It's a dummy variable anyway. And let's take it from n equals 0 to some upper limit. I don't know. Let's say, I'll just give it a different variable name. Let's say p. And we'll just have to set the slider in a second. Now, what do we have inside here? We said we have a sine of 2 times pi times 2n plus 1 divided by t. So 2 pi, and notice 2 pi divided by t, right? That's an omega. That's some sort of frequency. And then I will add in x being my variable. The last thing that we need to add in here is we need that scaling factor, the 1 over 2 times n plus 1. Okay. Now the nice thing here is that we are allowed, okay, so I'll set, the nice thing here is, there we go. I'm going to just leave t is equal to 1, the period, or yeah, the period, if you will. That's just to make life easy. Okay. We could change that if we wanted. And the second thing is, let's go ahead. I will include p going from 0 to, I don't know, 20 in a step size of 1. Now you notice initially, there's not much particularly interesting here. Okay. Let's, I'll go negative 1 to 1. There we go, just to scale it up for us. And why don't we go from 0 to 3? It'll just give us 3 full cycles. There, I'll get 4 in. Okay. So notice when p is equal to 0, I'm doing my summation from 0 to 0, so I have one single term, okay, the sine wave. And you notice that it doesn't have an amplitude of 1, but it's slightly less than that. That's the effect of that 1 over pi out front. We go ahead and we add in an extra term. Now we're adding a sine plus a cosine. Right? In fact, you can see this. This is sine of 2 times pi divided by t times x. Right? So you're adding out and with a negative sign in front of it, of course. T divided by pi. Okay. So the blue wave represents the sine function. Okay. And you can see that it's a little bit overestimated, or it's a little bit underestimated on the sides and a little, just slightly overestimated in the middle. So when you add this next term to it, this negative t divided by pi, sine of, now instead of 1, we have 3. So it'd be what, 6 times pi. Well, let's write it like this. 2 times pi divided by t. Okay. And then I'll put times 3, x. Okay. So that's that black line. And what's going on here? Let me get that out of the way for a second. Well, you notice that the blue line, the sine function, underestimates on the edges, and it's slightly overestimated in the center. So this next term has the tendency of raising the sides and lowering the center of the sine wave, which is why you end up getting, when you add these two together, you end up getting that extra little wiggle now. Notice that it's raised the sides of the sine function, it's lowered the center. Well, now you probably notice that the center's too low, the edges are too low, and these little red peaks are just slightly too high. So when we add our third term in, it's going to raise the edges even more, raise the center, and depress those two bumps. Okay. And what will end up happening as you keep going, you'll notice it keeps raising the underestimated parts, it keeps lowering the overestimated parts, and as you add more and more terms, this starts becoming more and more square-ish. Pretty cool, huh? Yeah, and in fact, let's go ahead now. This is the advantage to keeping the upper limit of the summation as a variable. We can just go ahead and I'll put it in as 50. Okay, so why don't we go ahead and now we can just play the video and I'll run it on loop. Okay, so it'll just go back, it'll go all to the end and start over. And so you can see as we add more and more terms, this thing looks almost exactly like a square wave. You might say, well, Greg, right at the edges, right where that's drop, you notice that you get that little spike. Okay? That's an artifact of the finite summation process. Okay? But you can, generally you can deal with that with some electronic filtering, for example. Okay? So you notice there's a couple of things that I'm missing here, and not particularly difficult to deal with. But the first one is simply the offset. So you can see that the offset is somewhere around 0.35. So I'm just eyeballing it right now. Okay, so let's say 0.325. There we go. So the offset was about 0.25. So I was missing that offset to go from 0. And you notice the other thing is that I'm missing a scaling factor, and I'm not quite sure where that's at. But once you have the general shape, the scaling is not terribly difficult. So if I scale it by I scaled it, I doubled the size, and then I'll offset it by 0.5. Now you notice that I get indeed the 0 to 1. So once I get the general shape, you can always finagle it to actually get the signal you want. Now, the reason I started off with this, first of all, is just because it is a fairly important signal that you would want to see in an electronic circuits class. Okay. The other piece, and I'll warn you, Okay. There's only about 4 or 5 different functions that are easily expressed in a what I call a closed form. In other words, that you can easily express with one term having this summation. Most of the time, if you get some sort of function, you won't be able to do this kind of simplification process. Okay? You'll be stuck essentially right about at this location. Okay? And then you'll have to do it on a term by term basis. It just so happens that sine has, or that square wave has an expression that's easily converted into a closed form. Okay? That's number one. Number two, oh, excuse me. And for completeness, I'll say that the typical 3 that you will see are the square wave, which we have just done an example of. Okay. The second one that you will see, and you probably already realize what's going to happen here, is the sawtooth wave. The function of t from 0 to, I'll put t less than t. Okay. You could say f of t equals t, something like that. And that will just give you a linear increase, and then it'll drop down, and it'll go back up and drop down. And of course, if you don't like that, you can always adjust the slope. And you can put an extra number here and change the limits just ever so slightly. Okay. So that's the second one. The third one is the piecewise triangular wave. Okay. Right? So for f of t equals t from 0 to big T over 2, and equals negative t from t over 2 back to t. Something like that. There might be an offset in there, but you have the general idea. Those are the 3 functions that are particularly easy to do a closed form expression. Okay. So it's not by accident that your function generator gives you those 3 options. Those are the 3 that are most common. Okay. Easy to do by hand. Okay? Okay, so there's that. The second piece that I will point out to you is that this representation in the time domain is not always the most convenient. Okay. Notice again, this is the time domain representation. Time on the x-axis, amplitude on the y-axis. Okay. A second convenient way to think about this would be in frequency space. In other words, what I will do is I will plot the amplitude on the horizontal axis, or excuse me, the vertical axis. And on the horizontal axis, I will plot my angular frequency. And so when my angular frequency was simply 2 pi divided by t, we'll set that equal to, we'll call that our base frequency, omega naught. So at omega naught, I have a particular amplitude. Oh, excuse me, it's negative. So at my base frequency, I have a particular amplitude. That's negative. And then my next one, I have some frequency at 2 omega naught. Well, 2 is even, and so I have nothing. Then I have 3 omega naught, which is smaller still. In fact, you get an idea. It's 1/3 the size of the first one. 4 omega naught, 0. 5 omega naught will be 1/5 the size of this first bar, height-wise. And so that is a different way of representing the same function. What you're doing is plotting, if you will, this amplitude, this 1 over 2p plus 1, as a function of this omega naught. And then notice that 2p plus 1, you get 1 omega naught, you get 2 omega naught, 3 omega naught, ... And here, I'll throw this up. so that you can see what the square wave will look like if you do this frequency plot, the amplitude as versus frequency. Cool, huh? And just for kicks, I'll give you a frequency plot for, say, the sawtooth wave. And you can see that it differs, right? Rather than it being every other term, all the odd terms and negative for the square wave, you see that the one for this the sawtooth wave looks different. Pretty cool, huh? Okay, good. So where does this leave us? Okay. Remember, we said a couple of lectures ago that when we're dealing with an AC source, okay, that doesn't have a single defined frequency, rather it has multiple frequencies, you can think of taking that AC source and considering each frequency individually. In other words, the total current is simply equal to the current due to frequency 1 plus the current due to frequency 2 plus dot, dot, dot. That's the first piece. Now, each of these currents will have their own amplitude as a function of frequency, and they will also have their own phase angle as a function of frequency. So each one of these has a slightly different amplitude and phase angle. Now with Fourier's theorem, we now see that we can take any function, any periodic function, and express it as that linear combination of cosines and sines. Which means that we can find the individual contributions of each cosine to a current, right? You could think then, okay, well, if I want to know these cosines, then I've got due to omega 1 plus due to omega 2 plus due to omega 3, dot, dot, dot. Okay? So it all comes back together. Now you have a method for turning a periodic function into a bunch of cosines, each of a different frequency. And you know that if you have multiple frequency source, if you will, okay, you can just think of the individual contributions. Now you're probably wondering, maybe, can Euler's relation, or not Euler's relation, can Fourier's theorem be extended? Yes, absolutely. So when I introduced Fourier's theorem, what I was doing is I considered cosine of 2 pi nt over t, for example. Okay. And I required that n be an integer. Said integer. Okay. That's actually an artificial restriction. Okay. This technique will work if you say that n is not an integer. Okay. For example. And the question is, let's say if n is not an integer, what happens to this expression? What do I need to do instead? Instead of summing, instead of a discrete summation, yeah, good. I'll have to do a continuous summation. Okay. In other words, rather than having a discrete summation, you'll have to do a continuous summation, something like a to the n. I probably shouldn't even have a to the n anymore. Maybe a as a function of n, cosine of 2 pi nt over t. And you would be integrating over that n right here. Or maybe even more compactly, rather than having 2 2 pi n over t, the period. More compactly, people will just write that as omega. Okay? And so maybe what you're talking about now is an integral of over omega, cosine of omega times t d omega. And there'll be some sort of, maybe there's a t over 2 pi, somewhere from u sub. We'll just lump that in with this constant a. Oh, but wait, there's more, right? You could always, if you wanted to, you say, well, this is ugly. I don't want to have to bother with that. I could always apply Euler's relation. And so, yes, you could just as easily do something like a omega e to the j omega t d omega. And that allows your amplitudes here to also, they'll probably pick up some imaginary components. Of course, what does Fourier's trick look like? Say you want to get a omega by itself. Okay. When we were talking about discrete n's, you had to do something like cosine of 2 pi nt over t times cosine of 2 pi p t over t dt. Okay. In other words, you had to take one omega, I'll call it omega n, a second omega, omega p, okay, and then integrate over time. So we'll have to do the same trick here, right here. Okay. If I want to get AW by itself, what I would have to do is f of t, e to the j, I'll call this one omega p t, integrated, that's a dt. And over here on the right-hand side, what I'll have to do is something like a times omega e to the j omega, I'll put n here, t, plus, oh, excuse me. How do I want to do this? Okay, yeah, I'll leave it like this. I'm sure that there's some, yeah, okay. You'll have to do j omega n t times j, I'll put a negative j omega p t. So I'll put a negative sign in the exponent. Okay. And then don't forget, now unfortunately I've got two integrals. I've got a d omega n integral, and I've got a dt integral. So I'll put the dt, and then I'll put the d omega n in here. And just like when you had two cosines of different n and p, you got 0 unless the two are the same. Okay. Similarly, right here, you will end up with, if omega n is equal to omega p, this will give you a value of 1. And if not, if omega n is not equal to omega p, this will give you a value of 0. Now, this is a fancy mathematical function. I won't go any further into it, but this is called the excuse me, I should capitalize, Dirac delta function. You'll see that pop up. But the end story is that you can still work everything out the exact same way. Okay? So you'll get something that says your amplitude at a particular angular frequency will be given by the integral of your function, f of t, e to the negative j omega p t dt. And sometimes, again, the only reason I put this in here is because this is sometimes known as a Fourier transform. All you're doing is applying Fourier's theorem and Fourier's trick. The only difference is that rather than limiting yourself to integer values, you can now take a continuous range of values. Yeah. I know that's a lot to kind of hang on to. Certainly, focus on understanding the integer value stuff. Okay. Go back through, watch the video, make sure you understand, okay, how we got the coefficients for the square wave. And in fact, I'll post it, but go ahead, take your stab at the triangular wave. Okay. It's good practice. Now, don't worry, you'll see it again. So you'll have time to practice it multiple times through your career. But I just want to get you started on that because Fourier's transform is a very, very important idea as well. Okay? You don't want to just limit yourself to integers. That's boring. Okay? We want the whole number line, if you will. Okay? Sweet. Okay. Well, I think that's enough for this video. I thank you for your attention. Keep up the hard work, and I'll see you next time.